Right now, somewhere above you, a commercial aircraft is cruising at 40,000 feet. The air outside that aircraft is minus 56 degrees Celsius. There is so little oxygen that a human being would lose consciousness in about 20 seconds without supplemental oxygen. The air pressure is roughly a quarter of what you experience standing on the ground. And two jet engines are running continuously in those conditions, producing tens of thousands of pounds of thrust, burning fuel at a rate of several tons per hour, spinning their internal components at speeds that would tear apart almost any other machine ever built. The question most people never think to ask is a simple one. How? The answer is one of the most remarkable pieces of engineering in human history, and understanding it changes the way you look at every aircraft you ever board. Let's start with the basic problem. A jet engine is essentially a controlled explosion happening thousands of times per second. Fuel is injected into a combustion chamber, ignited, and the expanding gases are directed out of the back of the engine at enormous speed. The reaction to those gases pushing backward is thrust pushing the aircraft forward. This is Newton's third law in its most spectacular application. But making that work at 40,000 feet requires solving a problem that sounds almost impossible. Fire needs three things to exist: fuel, heat, and oxygen. At 40,000 feet, the air is so thin that there is barely enough oxygen to sustain a candle flame. And yet, jet engines burn thousands of liters of fuel per hour at that altitude without interruption. The solution is compression. Before any fuel touches any flame inside a jet engine, the incoming air is compressed to roughly 40 times atmospheric pressure. The engine does this itself using a series of spinning compressor blades that progressively squeeze the incoming air into a smaller and smaller space. When you compress air, you also heat it. By the time the air reaches the combustion chamber, it is already extremely hot and extremely dense. You have effectively recreated sea-level oxygen density inside the engine at 40,000 feet. The atmosphere outside is irrelevant. The engine creates its own conditions. This is the compressor stage, and it is only one part of what makes jet engines extraordinary. A modern high-bypass turbofan engine, the type on virtually every large commercial aircraft, has multiple distinct stages working simultaneously. At the front is the fan. This is the large spinning disc you can see when you look at a jet engine from directly ahead. The fan is enormous, on some engines over 3 meters in diameter, and it rotates at several thousand revolutions per minute. Most of the air that passes through the fan doesn't go into the combustion process at all. It goes around the outside of the engine core, bypassing the combustion chamber entirely. This bypass air provides a significant portion of the aircraft's thrust, while also cooling the engine and reducing noise. The ratio of bypass air to core air is called the bypass ratio, and on modern engines it can be as high as 12-to-1. Behind the fan, the air that does enter the core passes through the compressor stages. A typical large turbofan has multiple compressor stages, often a low-pressure compressor and a high-pressure compressor working in sequence. Each stage has rows of rotating blades that accelerate the air and rows of stationary vanes that convert that speed into pressure. The air gets progressively hotter and denser through each stage until it reaches the combustion chamber. In the combustion chamber, fuel is injected and ignited. The combustion temperature at this point can exceed 2,000 degrees Celsius, significantly hotter than the melting point of most metals. This is one of the most remarkable engineering challenges in the entire system. The turbine blades immediately behind the combustion chamber must operate in gas streams that are hot enough to melt them. Engineers solve this through a combination of exotic materials. Turbine blades are made from single crystal superalloys that can withstand temperatures that would destroy conventional metals, and through cooling systems where air is routed through tiny channels inside the blades themselves, keeping them cool enough to function despite being surrounded by temperatures that would otherwise destroy them in seconds. The hot, expanding gases from the combustion chamber are directed onto the turbine blades. The turbine is the component that extracts energy from the combustion process. The spinning turbine blades are connected by shafts to the compressor stages and the fan, meaning the combustion process powers its own compression and airflow. The engine is largely self-sustaining once running. The fuel provides the energy, the combustion provides the heat, The heat spins the turbines compress the incoming air, the compressed air sustains the combustion, a continuous cycle running thousands of times per second at temperatures and speeds that would seem fantastical if they weren't meticulously documented and proven in service. After the turbine, the remaining exhaust gases are accelerated out of the nozzle at the back of the engine. The speed and direction of this exhaust produces the remaining thrust. On some engines, variable geometry nozzles can change shape during flight to optimize thrust for different conditions. The entire system, from fan to nozzle, happens continuously, simultaneously, in a space roughly the size of a large car engine, at altitudes where the outside temperature is colder than the surface of Mars in some regions. Now consider what happens when something goes wrong. Modern jet engines are certified to what engineers call ETOPS, Extended Twin Engine Operations Performance Standards. This certification allows twin-engine aircraft to fly routes where they are more than a certain distance from the nearest airport. ETOPS. 180 means the aircraft can fly routes where it would take up to 180 minutes to reach an emergency landing site on one engine. ETOPS 330 exists and covers some transoceanic routes. For this to be possible, the engines must demonstrate an extraordinary level of reliability. Modern high-bypass turbofan engines have in-flight shutdown rates of approximately 1 event per 100,000 flight hours. For context, a typical commercial aircraft engine accumulates perhaps 3,000 to 4,000 flight hours per year. An in-flight shutdown is an extremely rare event, precisely because the engineering that prevents one is so thorough. Multiple redundant systems monitor engine health continuously. Vibration sensors detect imbalances in spinning components. Temperature sensors monitor combustion stability. Oil pressure sensors track lubrication throughout the engine. Full authority, digital engine control systems, FADEC, manage fuel flow, ignition, and virtually every parameter of engine operation automatically, adjusting thousands of times per second to maintain optimal performance. A pilot can request a specific thrust level, and the FADEC will calculate and execute exactly how to achieve it, given the current altitude, temperature, airspeed, and engine condition. The oil system in a jet engine is a remarkable piece of engineering in its own right. Bearings support the high-speed rotating shafts at multiple points. These bearings must be continuously lubricated with oil that is itself cooled by fuel passing through a heat exchanger. The fuel absorbs heat from the oil and then enters the combustion chamber, where that additional heat improves efficiency. The oil and fuel systems are thermally coupled, each performing double duty, each part of a broader system designed with almost no wasted energy. Starting the engine requires external assistance on the ground. Compressed air from a ground cart or from the aircraft's auxiliary power unit is directed into the engine to spin it up to a speed where combustion can be initiated and sustained. Once running, the engine maintains itself. At cruise, the engine is in its most efficient state. High-altitude thin air means lower aerodynamic drag. The compression ratios are optimized for cruise conditions, and the fuel burn per unit of thrust is at its minimum. A modern large turbofan at cruise altitude can produce a pound of thrust for approximately half a pound of fuel per hour. This efficiency is why aircraft fly at 40,000 feet rather than lower. The thin air that seems like a disadvantage for combustion is actually an enormous advantage for aerodynamics and fuel economy once the compression problem is solved. The compressor solves the problem, and everything else, the turbines, the cooling systems, the FADEC, the redundant sensors, the single crystal blades, the bypass architecture, exists to make that solution reliable enough to trust with hundreds of lives over hundreds of thousands of hours of flight. Next time you board an aircraft and sit down and the engines spool up beneath you, you are sitting adjacent to one of the most complex and precisely engineered machines ever built. A machine that creates its own atmosphere inside itself, burns fuel at a rate that would exhaust a tank in minutes, operates in temperatures that exceed the melting point of steel, and does all of this continuously and reliably for thousands of hours between major maintenance events. The atmosphere at 40,000 feet cannot sustain combustion. The jet engine disagrees. and it has the engineering to prove it.